Next, we will see what are the standard test signals available. Why we use standard test signals? Generally, test signals are called reference signals and they are used to determine the performance of the system. How the system is performing, if you want to know, so we will give these reference signals. So those signals are generally called step signal, ramp signal, impulse or parabolic and so on. So using the information from these test signal response, we will use in designing the control systems. So in almost all the designings, so we have the responses. Those responses are either it a step response or impulse response or parabolic response and so on. We will start with the first signal, that is impulse signal. So what is the impulse signal? Mathematically we can define the impulse signal as, so we can see here, if R of t is my input, so if the R of t is my input, so R of t is equal to 0 when t is not equal to 0, when R of t is del of t at t is equal to 0. So t is equal to 0, we have R of t is del of t. So this del of t is nothing but your impulse. So what is this? Mathematically we will get the symbolically, if you take this as a time axis, then we have this as del of t. How can you define this del of t? So integral minus 0 to plus 0, this del of t is equal to 1, which means the area of this particular impulse is nothing but the infinite pulse. Basically it is a pulse. So if this pulse area is 1, as you try to move the time from 0 plus to 0 minus. So this is very useful. Impulse is very useful to find first of all to find the transfer function and also to know the stability of the system. So for most of the responses we'll see impulse responses to find the stability of the system. Now this impulse signal is also called direct Dirac signal, or we can also call it as weighing function, right? The reason why is a weighing function, because we can find out the transfer function, or if you know the impulse response, we can also find any other responses. Like I have impulse response, find the transfer function, again from here you can find any other response. So it is called weighing function. What will be the Laplace transform of it? So Laplace transform of impulse is always 1. So this is what the impulse signal is. Next is step signal. Mathematically we define the step as like this. Your R of t is equal to capital R when t is greater than 0, and this R of t is 0, t is less than 0. So when t is 0, generally your step signal is not defined, because if you look at the waveform, we look at the signal. So this is a time axis and we have this R of t. So till this 0, we have 0 only. At this 0 we have the value 0 as well as the R, where R is a step magnitude. So it suddenly increased and it is going to be there for long time. So this is what the step signal is. Step signal is called most dangerous signal out of all it, because we are suddenly increasing the value from initial value to final value and we are maintaining the value for long time. So let us say a fan is working on 230 volts, suddenly if you increase the voltage to 300 volts, and if you keep the 300 volts as it is, so it is very difficult to have the operation of the fan. Something like that, we have a step signal. So most of the responses we give the step signal. The step response, from the step response we are going to take the performance indices and we are going to look at how the system is performing. If the system perform for step signal well, then we can say that for all other signals system can perform well. Now, so what is the Laplace equivalent of step signal? Laplace equivalent of step signal is R of s is equal to R by s. If at all if R is equal to 1, then it is called unit step signal. So we can also call the step as permanent change or sudden change. Step is always called sudden change or permanent change, because the change is occurred and it is going to be permanent. Another thing about the step is, now we initially we take this is a 0 and we are increasing level to R. So this initial point need not be 0. Just now I gave the example, this can be a 220 volts and this can be the 300 volts. The difference between 300 and 220, that will be the capital R as a magnitude of your step signal. Now, so step can be positive, step can be negative, means from 300 it can come down to 220 also, that is called negative step. Now, so this step is also called positional input. Coming to the ramp signal. What is this ramp? Mathematically we define the ramp as R of t is equal to capital R into t for all t greater than or equal to 0, and R of t is 0, t less than equal to 0 or less than 0. So what will be the representation graphically? So we have this R of t and this is time, and if you look at your R of t from the mathematical definition, it is RT. As t is increasing, it is increasing like this. So this is a straight line which is passing through from 0. So this slope of it is the magnitude of the ramp. So how can you find the slope? You can take this line and this line, you can find out that ratio, that will be the slope. That slope is R, and which is the magnitude of my ramp signal. So ramp is considered to be unbounded signal, because as a t tends to infinity, my R of t value also infinity. Whenever the R of t value is infinity, t is infinity, under steady state condition, if the input signal is infinity, it is called unbounded signal. So practically we are going to operate the system, or we are going to give this kind of input to the system for long time. So generally we give a saturated ramp or terminated ramp. What will be that? So initially it increases and then we will have the step. The combination of the ramp, the combination of step is called terminated ramp or saturated ramp. Then what will be the Laplace equivalent? So Laplace equivalent is R of s is equal to R by s square. If at all capital R is 1, then we call it as unit ramp signal. So we can also call this a velocity input. Sometimes when you're talking about the steady state error concept, it is called velocity input. Similarly, we have another signal called a parabolic signal. How can you define mathematically? Look at here, R of t is equal to capital R t square by 2 for t is greater than or equal to 0, where this R of t is 0 and t is less than 0. So all the signals will appear only after t greater than 0, because in control system we always talk about the real time systems. In real time systems, so we should start always from t is equal to 0. We don't take anything t less than 0. Even the Laplace transform we apply, because the Laplace transform is applicable for from time 0 to infinity, 0 to plus infinity. So it is a one-sided transformation. That is the reason why we use Laplace transform in control system widely. Now, how the symbolic representation? So if you look at the graph, so graph R t square by 2, so it increases like this. So it look like your non-linear nature. Input itself is a non-linear nature, and as a t tends to infinity, my R of t is also going to infinity. So it can be called as a unbounded signal as it is. Generally, parabolic signal is used to find the steady state error, not to find the transient response. And here we can say this parabolic signal is as acceleration input. So step is a position input, ramp is velocity input, and parabolic is acceleration input. So if you list out all 4 input signals or standard signals: impulse, step, ramp and parabolic. So what are the R of s equivalent? Your R of s equivalent is 1, 1 by s, 1 by s square and 1 by s cube for unit, for example, for all the unit values. Now what is happening here? So impulse is 1. So if you integrate impulse, I am going to get the step because it is 1 by s. Whenever you have 1 by s, that is the integrator equivalent. Then again if you integrate the step, you will get the ramp, that is 1 by s square. Again if you integrate the ramp, you will get the parabolic, which is 1 by s cube. The reverse is also possible. So if you differentiate the parabolic, you will get ramp. Again you differentiate it, you will get step. Again you differentiate it, you are going to get the impulse signals. So these are the standard test signals that we are going to use to find the performance of the system.